Alright, and welcome back. In this video, we are going to be going through Chapter 8, Section 1, titled Similarity in Right Triangles. By the end of this video, we should be able to determine the geometric mean between two numbers, as well as apply the relationships that exist when the altitude is drawn to the hypotenuse of a right triangle. So let's have out our guide and notes. Let's begin. In this chapter about right triangles, you will be working with radicals such as root 19 and 2 root 5. A radical is in simplest form when the following three things occur. 1. No perfect square factor other than 1 is under the radical sign. 2. No fraction is under the radical sign. And 3. No fraction has a radical in the denominator. And radicals should always be expressed in simplest form. In example number 1, we are asked to simplify three given radical expressions. We have 3 root 98. That's the same thing as saying 3 times the square root of 49 times 2, because we are allowed to break up into factors underneath a radical. Once we break up the factors, we can break them up into two separate radicals as we are multiplying. So we have 3 times the square root of 49 times the square root of 2, or just root 2. We know the square root of 49 is 7, so we have 3 times 7 times root 2. And we can simplify down to get 21 root 2. In example number B, we're starting out with the square root of 3 over 5. We can break that up into the square root of 3 divided by the square root of 5. But remember, we're not allowed to have a radical in our denominator. So we're going to multiply by a value of 1. We're going to multiply by root 5 over root 5, because we're not changing the value, just the way it looks. And now we're doing what's called rationalizing the denominator. As we simplify, we get the square root of 15, because root 3 times root 5 is root 15. Root 5 times root 5 is root 25, but the square root of 25 is 5. So our two square roots of the same term underneath are going to now pretty much cancel out, and we're just left with a whole 5. For C, we're starting out with 18 over root 2. And remember, we're not allowed to have a square root in our denominator, so we multiply the numerator and denominator by root 2. As we simplify that down, we get 18 root 2 over 2, but we can simplify 18 divided by 2. 18 and 2 do not have a radical sign, or they're not underneath a radical sign, so we can operate them together. Root 2 is the only term, or the only piece of a term, that has a square root, so we are not able to operate with that. And we end up getting 9 root 2. With that in mind, let me move this. Whoopsie daisy. Please work on problems 1 through 15 on the guide and notes and resume when you're ready to move forward. So if a, b, and x are positive numbers and a over x is equal to x over b, then x is what's called the geometric mean between a and b. Notice that x is both means in the proportion. In example number 2, we're asked to find the geometric mean between the following two values. We have 12, we have 3, and 7 and 14. We're going to set these proportions up very, very similarly. We're going to end up with 12 over x is equal to x over 3 for a, and 7 over y is equal to y over 14. You could even use x. You could use whichever variable you want to here. We're going to cross multiply. So over on the left, we end up with x squared is equal to 36, and we end up with y squared is equal to 7 times 14. And that's not going to give us a perfect square. On the left-hand side, we can take the square root of x squared and 36, and we end up with 6. On the right-hand side, we have to simplify 7 times 14 as we take its square root, and as we do that, we end up with 7 root 2. So y is equal to 7 root 2. Please work on problems 16 through 20 on the guide and notes, and resume when you're ready to move forward. So if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. So if I were to construct a right triangle here, we have a right triangle, and if I were to draw an altitude, we would say, let's call this triangle 1, triangle 2, and this entire triangle is triangle 3. Triangle 1 is similar to triangle 2 and to triangle 3. Triangle 2 is similar to triangle 1 and to triangle 3. And triangle 3 is similar to triangle 1 and to triangle 2. So with this, please try it out. Please work on problems 21 through 23 on the guide notes, and resume when you're ready to move forward. To simplify stating postulates, theorems, and corollaries, segment, side, leg, and hypotenuse may refer to the length of these segments as well as the segments themselves. This is done in the following theorems. We have two theorems that we are going to go through. When the altitude is drawn to the hypotenuse of a right triangle, the length of the altitude is the geometric mean between the segments of the hypotenuse. This is why we're introducing geometric mean prior to this, because we can now apply it and say that the altitude drawn from the right triangle to the hypotenuse is the geometric mean between the segments of the hypotenuse. And likewise, when the altitude is drawn to the hypotenuse of a right triangle, each leg is the geometric mean between the hypotenuse and the segment of the hypotenuse. In the next slide, I'm going to be going through some examples here. So some examples and informational statements of these two theorems are given. We are given the diagram over on the right-hand side. We have a right triangle XYZ. We have a right triangle YAX and a right triangle YAZ. So if we look at our proportions on the left-hand side, we have XA over YA is equal to YA over AZ, because XA is a piece of the hypotenuse, AZ is the other piece of the hypotenuse. For the leg of XY, we could write it as XZ over XY is equal to XY over XA. It's the hypotenuse over the leg. It's equal to the leg over the piece of the hypotenuse that's adjacent to the leg. So if we're talking about XY, let's find my little marker here. We're talking about XY. We need to find the piece of the hypotenuse that's adjacent to that leg, which is going to be XA. The piece of the hypotenuse adjacent to the leg is going to be XA, because XY and XA share an endpoint. They share X. So they're going to be adjacent to each other. Now for leg YZ, or YZ, as I said earlier, that was weird. For leg YZ, we're going to have XZ over YZ, the hypotenuse over the leg, is equal to the leg over the adjacent piece of the hypotenuse. So if we again are talking about YZ, we're talking about in red right here, the piece that's adjacent would be AZ. So we can use this general setup to find the geometric mean, or to find the length of these legs here. In example number 3, we are asked to do that in two separate situations. So for A, if AN is equal to 4 and NB is equal to 9, we want to find CN. So the way we're going to set it up is AN over CN is equal to CN over NB. As we solve, we get that x squared is equal to 36, or we get the length of CN is going to be equal to 6. And for B, if AC is equal to 8 and AN is equal to 4, we want to find NB. Well, AB over AC is equal to AC over AN. So AN plus NB over AC is equal to AC over AN. Remember, AN plus NB is going to be the entire piece of AB. So we can simplify it down. 4 plus y over 8 is equal to 8 plus 4. We end up with 16 plus 4y is equal to 64. Subtract 16 on both sides, then divide by 4, and we end up having our length being 12. With this in mind, please work on problems 24 through 31 on the guided notes. You're doing a great job. This is not easy, so please make sure we are focusing in. Keep making yourself proud. Let us know if you have any questions. We'll talk to you soon.